So much as we did when we were talking about our kinetics of a particle, where we talked about our equations of motion, where we had F equals ma, and then we moved into work and energy before moving into impulse and momentum, we're following that same flow here with rigid bodies. So in our last few videos, we talked about our equations of motion and how to use our F equals ma, and our moments equals moment of inertia times angular acceleration. When we have problems where we're dealing with forces, accelerations, angular accelerations, those were really ideal to use those equations of motion for. But now we're going to start talking about, well, what if we use work and energy to solve these problems instead? So with your work and energy, you're still dealing with forces, right? You still have your rigid bodies that are either undergoing translation, rotation about a fixed axis, or the general plane motion, any of those. But now you have forces and you're more likely dealing with velocities and displacements. So instead of using those accelerations and trying to backtrack into velocities and displacements there, this makes it a little bit easier that you can solve directly with forces, displacements, and velocities. So that's why we like to use work and energy. And it's going to be really similar to what we saw in our kinetics of a particle, with just a few adjustments. So if we recall work and energy, when we were talking about our particle, we used kinetic energy. We'll talk about kinetic energy first. So when we talked about kinetic energy, we said T was the symbol we were using for kinetic energy, was going to be 1/2 times mass times velocity squared. So that worked for a particle when we had no rotational components. But now, since we have to account for rotation about a fixed axis, or for general plane motion, our generalized form of this kinetic energy is going to change a little bit. So our kinetic energy formula, the generalized form that we're going to use for this now, is going to be 1/2 mv squared, where this is the velocity of the center of mass g, 1/2 mvg squared, plus 1/2 ig, right? That's our moment of inertia, ig, moment of inertia of the center of mass, times the angular velocity omega squared. Okay, so 1/2 I omega squared plus the 1/2 mv squared. Right, both components, one accounting for the velocity, like translation component, and one component for the rotational velocity component. So this is our generalized form of kinetic energy, where if we have a translation problem, we can use that our kinetic energy is just the 1/2 mv squared, just like we did for the particle. Right, so just translating, if there's no rotation, we can still use that 1/2 mv squared. But if we have rotation, so like our rotation about a fixed axis, that's where we would want to use this 1/2 mvg squared plus 1/2 ig mega squared. And we can use this exact same equation for our general plane motion too. T is 1/2 mvg squared plus 1/2 ig omega squared. Or, if we want to, there is one other form that we could use for our general plane motion, and that's if we use the instantaneous center of zero velocity. Because if we use our instantaneous center of zero velocity, that would make our v term go to 0. So we could also use T equals 1/2 IIC omega squared. So only if we do that at that instantaneous center of zero velocity would it cancel out that velocity term. So these are generally, this is the general formula for any time we're going to use our kinetic energy now in our planar kinetics. We have to account for that rotational piece with the 1/2 ig omega squared. So that's our energy portion. For our work portion, it's still the same work that we had when we were doing work for a particle, right? So with our work, just as a quick review, we said the general equation for work was the integral from S1 to S2, so that's the displacement that you're moving across, that a force causes movement, right? That's the displacement F, and then if it's at like some angle, F cosine theta ds. So that's like if you had some box and you had a force at an angle of theta and it moved whatever distance delta s, right? So you integrate over that distance. That's our general form of the work equation, right? It's a displacement times a force. Our general form of the work equation. So work of a constant force is just going to be the force times however much it displaced it. Force times displacement. Other works that we had seen before, we've seen the work of weight. So the work of weight is going to be the weight times delta y. We've seen work from springs before. Work of a spring is going to be negative, in parentheses, 1/2 ks2 squared minus 1/2 ks1 squared. That's the displacements. Remember, those s's are displacements from the unstretched length. Your unstretched, your neutral length, whatever distance that was. S1 and S2 are relative to that unstretched length. And those were pretty much the general work forms that we had dealt with previously when we were doing our work and energy for a particle. And there is just one more work that we have to account for that we hadn't before, again, because of the rotation. So when we have something that's rotating and we have a moment applied to it, so if we have some general box there and it has a moment applied to it and it begins to rotate. So it was here and now it's here. It goes through this rotation angle of theta caused by a moment. So that rotation is still a displacement, right? That the displacement now, instead of being s, is actually an angle. It's been displaced through a rotational angle. So our moments do work now. We're going to have to account for that when we do our work and energy equation. So the work that a moment does is going to be the integral from theta 1 to theta 2 of the moment times d theta. So that's if you have a moment that's changing in terms of theta, or if you know that you have a constant moment, a constant applied moment, you can use is our moment times the theta. Where again, that's the angle that you're rotating through in radians. Okay, so this theta is in radians when you're doing this calculation. So that way you still get the same units of work, right? You're still getting pound-feet, right? Force times displacement, because that's what a moment is. A moment is a force times a displacement, right? It's just force times distance. And so work is too. So your work here should be the same units as your moment. So you have, pound-feet, Newton meters, whatever units you happen to be working in. Those are your moment times your theta in radians. That's what's going to give you the displacement portion for the work of a moment. It's also important to remember that some forces don't do any work at all. One of these that we have seen before, for example, is normal forces. Normal forces pretty much never do any work, right? They're always perpendicular to how this thing is moving. If a box is sitting on the ground and being pushed, the normal force perpendicular to the direction of motion, so it's not doing any work. Other things that might be a little bit newer, a little bit different, is if you have forces that act on like a fixed point of something that's rotating. So if you have, here this is a fixed point and here's a rod, and that rod rotates over this way, and this has forces on it, an Fx and an Fy. Well, those forces did no work to make this rotation happen. right? So those forces, you know, wouldn't be included in our work calculation here. So just remember that some forces don't do any work at all. It is only forces in the direction of displacement that do work. So with that said, let's do a quick little review of how to calculate our work before we jump into our problems using work and energy. Alright, so as you can see, we've got this bar here that has a lot of different things happening to it. So we want to find out what's the total work done on the bar below when rotated from an angle of theta equals 0 degrees to theta equals 90 degrees. Bar has a mass of 10 kilograms, and the spring has an unstretched length of 0.5 meters and always remains vertical due to the roller at B. The bar is pinned at A. Alright, so again, it feels like a lot. There's a lot of different things happening in this diagram. So we're going to break it down in our free body diagram left to right to kind of understand all of the forces on it and whether they're doing work or not. So we'll start out with our free body diagram. And this guy, you can draw him in a few different ways. You can draw him at the initial angle of 0 degrees. You can draw him at the final angle of 90 degrees. You can draw him as kind of an arbitrary in-between. And I think that's how I'll draw him since he's kind of given that way. So for any given angle there, from our 0 to 90 degrees, right? Because we're going to start at, gosh, I really did such a, I can't seem to complete this rod quite right. All right, there we go. So we've got this rod, and I'm just going to look at it left to right, see what I have going on. So it says I have a pin at A there. So a pin at A means I'm going to have a Y force and an X force there at the pin, right? That's support. It helps keep it in the wall and not just falling into space. So we've got an AX and an AY. As I travel on down, the next thing I see pretty immediately there is that moment. So my moment makes it into my free body diagram. And maybe I'll use different colors for all of these so you can see them a little bit better. So that AY and AX, those are my pin reactions. And if I go on down, I have that applied moment of 50 Newton meters that's causing the rotation through the angle of 0 to 90 degrees. And then if I keep going down, I need to remember that my bar has a mass and it acts at the center of mass, right? So this is a 3 meter long bar. It's going to act 1.5 meters down through the bar, right? At the midpoint of the bar here, and it's always going to act straight down. So my weight of my bar is going to be the 10 kilograms times 9.8, 98.1 newtons. Right, 10 times 9.8 gives me 98.1. And then if I keep on traveling down at 2 meters, I see that I get that spring. So we get this spring that it says is always going to be vertical because it's able to slide there in that roller at the top. So it's always going to remain vertical for the force in our spring. And they give us that spring constant there of 30 newtons per meter. And then as I go on and we make it down to the end here, the last thing that I see that I have is a load P. P is 80 newtons, and we see this is always perpendicular to the bar, right? That's what this little square is indicating to us right here, that P is always going to remain perpendicular to that bar no matter what the angle is. So at 0 degrees, P is straight down. At 90 degrees, P is going to be directly horizontal. So just know that those are what, that's what that's indicating to us. So now we've captured all of the forces on that free body diagram. Let's go ahead and just break down all of the work. So again, we'll move from left to right. So looking at our leftmost forces, we have AX and AY. So AX and AY do they do any work? The answer is no, they don't. AX and AY do no work. They do no work. Why is that? Because point A never moves, right? They act on point A there, but there's no displacement that they're causing. They're only there to hold that rod up in place. So AX and AY, they do no work. Don't need to account for those in our calculation. Our next one, as we kind of travel on down the line, is the moment. So that applied moment. And does that moment do work? And the answer is yeah, that moment does work. It is a constant moment, so the work of a moment that is constant is going to be m times delta theta, whatever theta it's moving through. Oops. So here we have the moment of 50 times the theta it moves through is 90 degrees, and remember that theta has to be in radians. So 90 degrees is pi over 2 radians. So that gives us that the work from our moment is 78.5 joules. Right, that's Newton meters. Newton meter is a joule. Let's keep on working down the line here. We have our weight, right? And our weight is doing work because this bar is swinging down from a horizontal position to a vertical position. So our weight is doing work. Our weight is initially, if this is our bar, we're initially here. And then our final state is here. So that delta y is that change from initial to final there. So our weight does do work. The work of weight is weight times delta y. And it assumes that the delta y is going down for a positive work here. So that's going to be our 98.1 times the distance that it displaces downwards of 1.5, right? Because we said that our location of it is 1.5 meters. So when it swings from the horizontal to a vertical, it displaces, that weight displaces by 1.5 meters. Like that point, that G right there, center of mass G, displaces by 1.5 meters in that vertical direction. That gives us a work of 147.2 joules. And then as we keep on going down the line, we can see our spring, right? Our spring force there. And so spring does do work. That spring is being extended as the bar goes lower and lower. So our spring does work. And U spring is going to be negative 1/2 ks2 squared minus 1/2 ks1 squared. So I'll bring this down a little bit farther. So this is going to be negative 1/2, and then our k they gave us was 30. And then remember that S is the difference between the unstretched length and its final length. So its final length, when this is in its vertical position, vertical position is the ending length. Our spring force, our spring is going to be right here, and this distance from, let me do it from, not to the top, but from where the spring ends to where the spring starts is going to be this 2 meters plus this little region that's above A, right? So there's a region where the spring is stretched out like above the horizontal. Because if we have it in the horizontal position, your spring is right here and you still have this 0.75 meters to contend with. So your S2 is the 2 meters plus that 0.75 and then minus the unstretched length. So what was the unstretched length? Unstretched length is 0.5 meters, so this is going to be 2.75 minus 0.5. Right, so 2.75, that's the total length of the final spring minus the unstretched length. And we're going to square that. And then we're going to minus 1/2 times 30 times the initial length minus the unstretched length. So initially, when the bar is horizontal, it still has that 0.75. Like, it's still experiencing a little bit of stretch because unstretched is 0.5. So it still experiences that little bit of stretch. So 0.75 minus 0.5 squared. All of that gets popped into a calculator, and that's going to give you negative 75 joules for our spring there. And then our very last one, that P load, right? That constant load of P at the end of the bar there. So since it's a constant load, we know it's going to be, oops. So call this load P. The work of a constant force is just the force times the displacement. Remember, it's the displacement in the direction that the force is going in. So when we have this P, when the bar is horizontal, P is acting downwards here, and then as it travels, P keeps acting perpendicular to the bar until you get P like this. So P is constantly perpendicular to the bar, and you're going to see that the displacement path that it goes through is a semicircle. Not a semicircle, it's a quarter circle. But it goes through a circular arc pattern, right? Because it's always perpendicular, it's always acting tangent. That path that it's swinging through, it's swinging around there. Which means that our displacement, that S value, is actually related to this arc length here. Right, where we have S equals theta times R. Where we know the R is the length of the rod, and the theta is that 90 degrees it's going through, that pi over 2. So pi over 2 times the length of the rod is 3. And that gives us our S value. So here it's going to be 80 times pi over 2 times 3. And that's what gives us our work of that constant force, 377 joules. And then finally, to get your final answer, we're just going to add all of them together. So take your total work is going to be 78.5 plus 147.2 minus 75, since that's a negative, or plus a negative 75, plus 377. So the total work, 78.5 plus 147.2 minus 75 plus 377 is going to give us a total work of 528 joules. Right, so just a little refresher that our work is only the displacement, or is only the force times the displacement. It's the force in the direction of displacement there. Not all forces do work, and we do have moments that we need to account for because of our rotation. Moments can do work as well. So in our next video, we're going to go ahead and look at our principle of work and energy, just as we had in kinetics, or in our kinetics of a particle. We have it in our kinetics of a rigid body. And then we'll also look at our conservation of energy. So these are really going to mirror what we saw with a particle. Now just have this little bit different application with our rigid bodies, since we have the rotation to account for. And we'll go ahead and take a look at those in our next videos.